And welcome back, students. Today we are going to be getting into Big O notation. So we're going to start by asking, what is Big O? So it could lead in with an introduction to algorithm analysis. First off, let's ask, what is an algorithm? And we have kind of discussed this term before. But an algorithm, if you recall, is a set of precise instructions to solve a problem. When looking at evaluating how strong our algorithm is, we want to look at two things. First off, the speed. How quickly can the algorithm complete the task? And when we're talking about speed, we're not talking about seconds or minutes. I mean, yeah, it might take that, but generally speaking, we're looking at even down to the millisecond or the nanosecond. Memory. How much system resources are needed to complete the task? You might have an algorithm that's super fast, but takes a lot of system resources, and so you would need a much more powerful machine. When we look at analyzing an algorithm, there are several different algorithm complexity analysis methods. There's big O, there's big omega, big theta, small o. There's a bunch of them. For our purposes, though, we're primarily going to be looking at big O. As mentioned previously, there are two components when evaluating an algorithm: speed and memory. These can be translated into two different types of analyses: time complexity analysis and space complexity analysis. So it's still tying back to the speed and memory that we talked about earlier, that they're now giving a more formal name. Let's talk about big O notation orders. As we examine big O and its complexity, we'll be examining algorithms and determining their effectiveness. The table on the next page shows some common big O notations and their name. So in here, this is a table that you might want to get to know and love. I have several different examples in here. Only one that's not really in here is the square root, but it would fall right in here. So for example, you have big O1. That's a constant. An example of that would be a hash table, and it remains constant regardless of the data set size. So whether you have 100 items or 1,000,000 items, the rate of how long it takes to work through that is the same. We have big O of log n, which means it's logarithmic, which means that is, for example, binary search. It increases by constant. If n doubles, the time to perform increases by constant smaller than n amount. We have big O of n, which is a linear. So this would be like a linear function. Finding an item in an unsorted list would be an example of that. It increases in proportion to n. If n doubles, the time to perform will double. We have big O of n log n. So the type is n log n. Examples of that are quick sort and merge sort. So it increases at a multiple of a constant. Big O of n squared, that's a quadratic. Example of that is a bubble sort. It increases in proportion to the product of n times n. Then we have big O of c to the n. That's an exponential function. Examples of that would be the traveling salesman problem, but it's solved using dynamic programming. The description of that is that it increases based upon the exponent n of a constant c. And then lastly, we have big O of n factorial. So this is again the traveling salesman problem, but this is now solved using brute force, and it's going to go through every single possible combination, which means that in turn that it's going to increase in proportion to the product of all numbers included. So the bigger you get it, the more terms you're going to have to multiply to figure out where it's at. And n factorial is obviously going to be one of the harder things to try and solve here. So here's a quick visual representation of some of those. In here you can see we have big O of 1, and you can see if we have very small data sets, big O of 1 is not necessarily the fastest. But if you look over it as you look as the data sets get larger, big O of 1 is the ideal situation to be in. If we have big O of log n, you can see that that's considered then to be the next efficient one. Big O of n log n we don't have in here, but we do have the square root of n, and you can see it falls right here between big O of n and big O log n. We have big O of n squared, big O of n cubed, just as another example. And we have big O of n to the power of n. Right, so these are all some different examples here of different things. If you had n factorial, it would also be coming along right in here. It would be writing really sharply because it's one of the least efficient algorithms here. And of course, if you had n of c to the n, that would also fall here somewhere where like n to the n is. All right, let's ask though, why do we want to know about big O? Well, big O notation is used to determine the upper bound on the growth rate of a function. We're not looking at the lower bound, we're not looking at, the middle, we're looking at the upper bound. So this, in a way, is used to determine the efficiency of your algorithm. How efficient is it? For example, the time or the number of steps it takes to complete a problem of size n might be found with the function rule t of n equals 4n squared minus 2n plus 2. So that's a polynomial function. As n grows large, the n squared term will come to dominate so that all the other terms can be ignored. So pretty much what this is saying is that as that n squared, as you start plugging in larger and larger numbers in there, the n squared really takes more prominence than the 2n or the 2 because it's the most powerful piece of that growth factor. In fact, if you ignore the latter part of that equation, it's going to have a very negligible effect on the expression's value for most purposes. Further, even the coefficients will become relatively irrelevant if we compare it to any other order of expression, such as a term containing n to the third or n to the fourth. So really when we start looking at these, that's why if you look at the big O notations, they're really kind of just looking at the parent function form, because at the end, that's the form of the function that's the most powerful and is going to have the most influence. And that's exactly what we just said here. So that the parent function used to determine the big O notation. So in this case, this example is falling under big O n squared. And that concludes our notes, folks. Until next time.